Yeah. Okay, so today we did an area between functions. Not a terribly hard skill, flows straight on with what we've been doing, but you will start to see the complexity of the problems increase. So this is it here, like rather than just finding the area under a curve, now we're finding the area between two curves. And so your first diagram is there is we have g of x being some function and f of x being some function over the top of it. And the area between them, let's say they intersect at a and b, the area between them is the integral of a to b of the top function, always the one that's on top, take away the one that's on the bottom. Okay? So here we have, find the area between y equals x squared and y equals 4. So first we need to find the points of intersection. That's where we're going to graph the function over, or what we're finding, the interval over which we're finding the area. So we could graph it and g-solve them. Or we know that functions intersect when they are equal to one another. So that's going to be when x squared equals 4. Alright, so this is the first function. It's the equation of the horizontal line, y equals 4. Every x value has a y value of 4. And then the other function we're talking about is the basic quadratic y equals x squared. So when they're equal to one another, that's going to be the values that we're talking about. We square root both sides, and we get x plus or minus 2. So our lower boundary is going to be minus 2, and our upper boundary is 2. So here's the integral we're going to perform then. We're going to perform the integral from minus 2 to 2 of the top function, which is 4. Okay, take away the bottom function, which is x squared. So here's a little trap. Make sure you put g of x in brackets, okay, so that the negative distributes to any terms that are in there. And then with regards to x, we'll integrate. So we'll have 4x, take x to the 3 on 3, minus 2 to 2. We'll put the information in there. Bonk. So that's going to be 4 times 2, take 2, 3 and 3. Okay, so there we've put 2 in, and then over here we're going to put minus 2 in. Okay, so use brackets appropriately. Alright, and from there you've shown sufficient evidence to just perform the calculation in your calculator. Okay, you can evaluate that part in your calculator. Or we can go through and simplify it manually. So what have we got here? We've got 8, take 8 on 3, and we've got take minus 8, and take minus, and this is going to be minus 8 on 3. Okay, so what does that become? We've got 8, take 8 on 3, plus 8, and then here we've got plus minus 8 on 3. So we've got 16, take 2 lots of 8 on 3, 16, take 16 on 3, what's that, 48, take 16 on 3, 32 on 3. Alright, so much quicker than just punch it in your calculator, but there's how we're generating the solution. Okay, let's move on to B. Find the area enclosed by the y-axis, the x-axis, and the function e to the x take 5. So, if we were to draw this function, okay, e to the x looks like this, doesn't it? That's an exponential function. And so if we're going e to the x take 5, that's going to move it down 5 units. So it's going to look something like this. Okay, this is e to the x take 5. Okay, let's not get caught up with these fine details here. Like the process is the important part, and then you can crunch that kind of thing in your calculator. Let's focus over here. So we've got, like you might be going, well I only sort of have one function here, e to the x take 5. But what we can do is this line here, or the x-axis, okay, that's the equation of the line y equals 0. It's a horizontal line, it's y equals 0. So now we have a top function, y equals 0, and a bottom function, e to the x take 5. we need a horizontal boundary over which we're going to integrate it from. Now, the restrictions we're given are the x-axis, the y-axis, and the function. Okay, so it wants us to find this area in here. So obviously this x value is 0, so that's going to be the lower boundary of our integral. And then we need to find the upper boundary of our integral. Okay, we're going to find it exactly. It probably says find the area exactly. So the upper boundary, we need to know what's the x-intercept of this function, e to the x take 5. What is the x-intercept of e to the x take 5? X-intercept occurs when y is 0. So we have e to the x take 5 equals 0. And then we'll go ahead and solve this. E to the x is 5, and then we'll put the natural logarithm on both sides. Okay, so that means our upper boundary is ln of 5. Okay, so we've identified the area we're solving, we've found the lower and upper boundary, and now we're ready to make the statement about the area that we're finding. Okay? The integral we're going to perform is the integral from 0 to ln of 5 of the top function take the bottom function. What is the top function? It is the equation of the line y equals 0. So this is the top function. Okay, anytime we're asked to find area under the x-axis, the top function is 0, and then take away the bottom function is this one here, this curve, e to the x take 5. With regards to x, and that's going to be the integral that we perform. So let's see. 0, that's nothing. So then over here we're going to have minus e to the x, and then plus 5x. Okay, let's put our information in. Over here we've got minus 1, that's 0, and then we have take minus e to the ln 5, so that becomes plus e to the power of ln 5.
Is it the other way around? Is it ln first?
Yeah.
Oh yeah, thank you. Yep. So, like one way I can fix that is I'll just put the plus there and the minus here. Okay, so what are we going to have? We're going to have 1, that's 0, then here we've got take e to the ln 5 and plus 5 ln 5. Okay, so minus e to the ln 5, that simplifies to be 5. So we've got 1 take 5 plus 5 ln 5. What have we got? We've got 5 ln 5, take away 4. Alright, so we've found the area exactly. Units squared. Okay, so yeah, how will I describe that? We put the ln 5 in here, that's this part here, and then we'll put 0 in over here. Okay, it's ln 5, take away, and we put 0 in. So what have we done? We found the x-intercept, we found the boundary over which we're integrating it, we made a statement, top function take the bottom function. Okay, so that's the new part, and then we perform the process. Jump up over here. Alright, next one. Find the area enclosed by the x-axis and sine x over the interval 0 to 2 pi. So if you sketch the sine function, this is what it looks like. Okay, here's 2 pi, here's pi. Like you can check that on your calculator. Now if we want to find the area, it's not enough to go, oh well, we're going to find an integral from 0 to 2 pi of sine of x. Okay? If you put this in your calculator, If you say, what is the value of this? It's going to say 0. Why?
They cancel each other out.
That's right. These regions have the exact same area. Okay? They're symmetric about the x-axis. And so when we calculate this area, right, that's going to be a positive value. But then when you calculate this area, it's going to be a negative value because it's below the x-axis. If I asked you to calculate this area separately, you would recognise, well, we have to have a top function and then take away the bottom function. All right? And so that's how you get around the negative issue when you calculate an area below the x-axis. So that means there's 2 ways we could do this. There's sort of a long way that makes a lot of sense, and then there's a short way that also makes a lot of sense. So I'm going to demonstrate both parts, and then we'll choose one. So the first integral that we could perform is the integral from 0 to pi of sine x with regards to dx, and then multiply it by 2. Okay, and that's the path we'll take in a moment. All right, we'll just calculate one hill, and then times it by 2 because we know that it has the same area over here, same horizontal distance, same vertical distance that it traverses. That's what we're performing. The other way that you might think of might be the way that's following on from what we've been doing is a cumulative sum of 2 separate areas. So it would be the integral from 0 to pi of sine x, all right, plus the integral from pi to 2 pi. So then we're just looking at this region here, pi to 2 pi, of the top function. Okay, in this case the top function again is the x-axis. The x-axis has the equation y equals 0. Of the top function, take the bottom function. Okay, so if you were to perform this integral, you're going to get the exact same answer as we do over here. Let's smash this one out, it's going to be nice and easy. Integral of sine x is negative cos x. And put the pi in. So negative cos of pi, take negative cos of 0. Alright, now cos of pi is minus 1. And here we've got cos of 0 is 1. And so let's have a look at this. We've got minus 1, which is positive 1. And then take minus 1 plus 1 as well. So one of these loops has an area of 2 units squared. Okay, if we said what's the area from 0 to pi? Well, it's 2 units squared. So therefore the area from 0 to 2 pi is 4 units squared. Good. So there will be problems, right? There will be problems that later on, they come a bit later on, where you do have to perform multiple sums. Okay? Probably in about 20 minutes, I'll show you guys a bit of a calculator trick that we can help use our calculator for these ones. And we would like you to work through it predominantly in a manual manner. Okay? Cool. Friday Arbor. Let's get into it.
So if you had more of those